Well, it's a great pleasure to be here at this meeting to commemorate 50 years since the publication of Alan Brewer's paper. I'm also very pleased to be here back at the department where 27 years ago I started my atmospheric science career, and it's kind of scary to think that 27 years is actually, more than half of this period that we're talking about. The same thing happened to me a couple of years ago when I went with a student to the railway station in Cambridge, and I realized that actually the distance in age or in years between my getting an old person's rail card and a student rail card was considerably in favor of the former.
Historical review now.
I am indeed, and I'm very sorry Phil Goldsmith isn't here, because I wanted to say a few words about my viva. I'd done some work on modelling ozone in a two-dimensional model, and we'd found, amongst other things, this miraculous balancing between the mean transport and the eddy transport that Jim talked about earlier on. But Phil was my external, and those people who are not from Oxford won't realise that when you have a PhD examination, you have to turn up in what's called sub-fusk. That's to say, you have to wear a gown, you wear a dark suit, a white shirt, and a white bow tie. And my internal examiner was John Horton, and we met in a room down here. And it was a warm day, and John said, "I think we can take our jackets off." So I took my jacket off and put the gown back on. Phil Goldsmith, of course, had turned up in a kind of tweed jacket. So I said to Phil, "I see, Phil, you're not in sub-fusk." And Phil looked at me and he said, "Watch it, lad." So this didn't completely lighten the mood at the beginning of the viva. But actually Phil was great, and he did relax me, and we had a really good examination. And at the end of the examination, or near the end of the examination, Phil, who'd done a lot of work on aerosols, said to me, "Aerosols and chemistry in the stratosphere, do you think there's any kind of importance there?" And I said, no chance, really. And I think Phil said, or at least I thought Phil said, "Yeah, I agree with you, lad," you see. I reminded Phil about this 2 days ago, and he said, "No, I didn't say that." He said, "What I said is, you might be right, lad." Very typical Phil Goldsmith. Okay, I want to talk about two things. One is Northern Hemisphere ozone loss, and say a few words about the middle latitudes. This is a study using the SlimCap model that Martin talked about this morning. The person who's been doing most of the runs is Marianne Guillet. Martin, of course, has been very heavily involved, and also another student of mine, Panos Hadjinikolaou, has done some of the work that I'll talk about. The other thing I wanted to do, everybody's been talking about the 1949 paper, but for me, because I got interested in ozone, this is a really good paper. I mean, Alan talks about the difficulties of getting that paper published, and it has some really good contemporary ideas for anybody now. In particular, and I'll say a little bit about this later on, it's extremely good at talking about the importance of timescales in the atmosphere, the importance of balancing timescales between chemistry and transport. And I was thinking about this with this meeting in mind, and I have an undergraduate, we now have a Part 3 in Cambridge, 4-year course, and I have an undergraduate who's been playing around with the trajectory model with this sort of Brewer and Wilson idea in mind, and Helen Rogers has been helping her. So I want to say a few things about that at the end. So let's try and get on. You're all, I guess, familiar with this kind of picture showing the trends in ozone. I'm going to say a little bit about trying to model ozone change, and in particular the fact that we see quite a lot of change during the 1990s in high latitude ozone. And also I want to say a few things about what's going on in the middle latitudes. And one of the problems, and it's been alluded to already, is in a sense the difference between the interannual variability and the trend. And I guess what I'm going to be talking about more is this interannual variability. This is the same thing, but let me show you the trended stuff. This is two plots from the recent WMO NASA report, it's total ozone adjusted for seasonal solar and QBO effects, 1978 through to 2000. The top is satellite data, the bottom is ground-based data, and you see this kind of downward trend, but you see an awful lot of interannual variability. And in particular, for example, we see this low ozone immediately after Pinatubo in 92, 93, and then somewhat higher ozone in other years. And as Lauren's just said, if we're going to be able to predict, or if we're going to have confidence in predicting how ozone recovers, we have to explain, I think, not only the trend, but also this interannual variability. And people have tried to do that. And people have offered all sorts of different explanations, both chemical and dynamical, as to what might be going on. This is some work from Susan Solomon and her colleagues. We're looking at 45 degrees north, the ozone anomaly from 1978 through to 1997. It's a 2D model. If you just put in chlorine trends, then you get this. But the data is the black triangles, for example, the TOMS data, and you see that the model doesn't capture that. But if in their model they include the fact that there was a lot of aerosol after Mount Pinatubo in 1992, and also after El Chichon, indeed, in 83, I think, then when you include that, and you also include some measure of the variance of temperature, then they get this green figure here, which agrees much better with the data. But when I saw that, I still felt, harking back to the vibe with Phil Goldsmith, that maybe this wasn't really the whole story. And there have been other chemical explanations that I think, over and above this, also offer to try to explain this. Lots of chemical explanations about, but it seemed to me that it wasn't necessarily just chemistry that was going on. And in particular, for example, again, as a research student, I'd looked at, I think Reggie Newell had looked at what happened to ozone after Mount Agung. And the kind of ideas then were that the circulation had changed because we put a lot of aerosol into the low stratosphere. And it seemed to me conceivable that that was at least part of the story in what was going on here. So I got one of my students to do some integrations with a very simple chemical scheme. A little bit like Kevin Hamilton was saying this morning, this chemical scheme knows nothing. It's the Carriol ozone relaxation scheme. So it knows nothing about changing chlorine in the atmosphere. It knows nothing about changing aerosol in the atmosphere. And we ran the SlimCat model for 5 years with 3 different sets of meteorology. We ran in green with the meteorology from 1992-93, in red with the meteorology from 93 to 94, and then we ran a run which used the meteorology from each year from 92 through to 97. So a chemical transport model forced by different circulations. And we did these 2 runs with 92, 93 repeated and 93, 94 repeated to convince ourselves that there was no drift in the model, which is essentially true. What you see, first of all, is that there's a big difference between using the 92-93 meteorology. This is ozone at 47 north, and the 93 and the 92-93 meteorology. Much lower ozone in the model in 92-93. And when you do the long integration, using the stuff from each year, then you do see, for example, low ozone in 92-93 post-Pinatubo, and much higher ozone, for example, in 93-94, as observed. In other words, this is not a chemical signal. This variability is being driven by changes in the circulation. Okay, that was a simple chemical scheme. I'm going to come back to that in a minute or two, but as Martin showed us this morning, we've done a lot of integrations with the SlimCat model. Martin talked about a long integration. Here, I'm going to say a few words about some seasonal integrations that we've done each season at somewhat higher resolution than Martin showed. So these were all integrations that started, I think, at the end of November, and this is for 95-6 through to 98-99. 2 of these winters, 5-6 and 6-7, were pretty cold, and you can see that this is active chlorine, averaged polewards of 75 degrees north. In those 2 winters, you get quite a lot of chlorine activated when the temperatures dropped, and they stay up for a long time. 97-8 and 98-99 were warmer winters, but they had occasional periods when it was cold to activate some chlorine. An interesting chemical thing here is that the deactivation process depends very considerably on time of the year. This is deactivation happening in the late winter, early spring. and this is the sort of deactivation rate. So it was cold here, but then it really very little reactivation. And you can see the deactivation rate in midwinter, less photolysis, less photons around, is much slower. Rather interesting. And to confirm what Martin showed earlier on, these are the ozone losses on this 480K surface polar at 75 degrees north for the 4 different winters. And the surprising thing in a way, and Martin said this already this morning, is that there is variability in the loss, but it's, I think, not as big as we might have imagined. In some winters, the 2 cold winters, we're seeing perhaps approaching 35% loss on this surface polar of 75 north. But even in the warmer winters, we're getting a reasonable amount of loss. What we've tried to do in those integrations is to look at what's going on in the middle latitudes. And just to kind of recap, and let's just look at the bottom figure here. This is the modelled ozone depletion north of 75 degree north equivalent latitude on the 31st of March in 3 winters, 5, 6, 6, 7 and 7, 8. And the bottom, these are different potential temperature surfaces. Cast your eye on this partial column between 350 and 670K. What you see is that in the 2, I'm just looking at 2 of the winters, in the 2 cold winters of 5, 6 and 6, 7, we've got quite large ozone depletion. 96, 97 had a strong, stable vortex that lasted a long time. And we've got something like 80 Dobson units loss. Whereas in the somewhat warmer winter of 97, 98, we've only got 53 Dobson units loss. Okay. If we now look at the loss average north of 40 degrees north, so this is from 40 north all the way to the pole, so we're including the polar loss as well, then what we find is 5, 6, 6, 7, 7, 8, cold winter, stable vortex. This has actually got, when we integrate from 40 north to the pole, this has got the lowest loss of those 3 winters. And to me, this was kind of a bit like, to borrow a phrase from Arthur Conan Doyle, this was the dog that didn't bark. Something strange happening here, because we've got lots of heterogeneous chemistry going on inside the polar vortex, and yet when we average over the whole of this latitude belt, then we've got rather low ozone. And it seems to me, and I don't completely understand what the implications are, but it does seem to me that there is a big message here about the connection between what's going on in polar latitudes and what's going on in middle latitudes. To investigate that a bit more, we went back and we then took out the heterogeneous chemistry. So we didn't allow any heterogeneous chemistry. Essentially, we didn't allow any heterogeneous chemistry. And the results that we then got inside the polar vortex are shown here. And there's difference between 30 Dobson units and 37 Dobson units. Remarkably little difference. Obviously a big change in this winter and changes in all the winters, but considerably less ozone depletion, as you'd expect, of course, if we say there's no heterogeneous chemistry going on. And here we are. If we do the same thing, we then look at the middle latitudes, then again, remarkably, the difference in the calculated depletion where we don't have heterogeneous chemistry going on now becomes quite small, and we have a relatively small change in the winter of 96, 97. In other words, it's not made a huge difference, but there's a much larger difference in 95, 96. And as I say, I'm not completely coherent in my explanation of what's going on, but I do think that what's happening for example, in 95, 96, there was a cold but rather disturbed vortex, a lot of activation on the edge of the vortex in that winter, and I'm sure we were getting a lot of air out into middle latitudes, if you like, processing, which was then leading to middle latitude loss. And that's why we see this big change here. Whereas in 96, 97, there was a much more stable vortex, and I think therefore much less influence of the polar vortex on middle latitudes, as shown by this rather small change that we've got over there. So, how long have we been going for?
Oh, you got 10 more minutes.
Right, okay. So, to kind of, in a very sort of hand-waving kind of way, I'd say, that certainly what we seem to see is that in certain cases we are seeing ozone loss which is confined to polar latitudes, but in these warmer, less stable vortexes, clearly though in cases where we have temperatures which are cold enough to produce, to initiate some heterogeneous chemistry, then we see loss over a wider area. And I believe that it's not just dilution, but it's dilution plus movement of activated air into the middle latitudes. Okay. That was that. And as I say, what I wanted to do was to recommend to you very strongly that you look at this paper by Alan Brewer and Wilson. It was published in the Quarterly Journal in 1968, and it talks about the regions of formation of atmospheric ozone. The chemistry scheme that was used in here, it was a Chapman chemistry, but as I say, I think that the ideas in it about the way that parcels of air move around and the influence of chemistry on those parcels of air, I think are as relevant today as they were when this paper was published. What they considered were three regions of the atmosphere: one at high levels where the ozone equilibrium timescale is short, an intermediate region, and then a lower region where, if you like, the photochemical timescale is long and transport dominates. And they point out in this paper that the depth of this middle box might be quite small, and these three regions correspond to regions where the equilibrium time, well, I've said that already, long, comparable, and short. And Alan talked about this on Monday. On entering the upper box, the parcel of air will be close to equilibrium, and it doesn't really matter what you do. You know, you can move it around there as quickly as you like, but because the equilibrium timescale is so fast, it's always going to locally adjust to photochemical steady state, and therefore, really, it isn't going to have a huge significance on what happens elsewhere in the atmosphere. And they make the point that what really is important is the production of ozone is at lower levels where the equilibrium time is long and, if you like, comparable to the dynamical time scale. And the net production, you know, will occur in this intermediate box. It's in some doubt, and so on and so forth. Really nice paper, and as I say, those of you that haven't read it, you really ought to. This is pardon?
Lucky we got it published.
Absolutely. No, I think that was well, I think you've got the message. Okay, so this is from that paper, and I'm sure the picture would be different now, but basically what they were saying is that there is this region here, you know, photochemical equilibrium over here. We're not really that bothered about what's going on, if you like. And then there's a region over here where, as you move air through it, then this is really going to be important for what goes on down here, where the chemical timescales are quite long. And this got me thinking, and indeed I've been thinking about this for ages, but doing nothing about it. About, you know, how can we use this to understand? Can we use this to understand trends in ozone? If there is a change in the circulation, if there is a change in the rate at which we're moving air from this frozen equilibrium state through it into the state where the chemistry becomes very long. If we have those changes, can we get changes? You know, can that explain parts of the trend that we're seeing? And I don't know the answer to that. Well, I guess the answer is yes, but I'm not going to be able to necessarily convince you. But what we have done, this is what this undergraduate has been doing, is so far we've looked at completely idealized trajectories. And all we're doing is we're moving air from here to here by different paths. And the only thing they all start off with the same amounts of chemicals in here. They all finish up here at the same time. But we move them by different routes. And what we'll do next term is actually to try to do this with some real trajectories. So far, this is what's been done. And there's no mixing at all. And yet these parcels are running for quite a long time. So this is, in many ways, you know, quite unrealistic. But I hope it might be instructive. So what we've got is A stays aloft the longest before coming down, and then we move through parcel B, C, D, E, F, G, which comes down most quickly and then moves this way. And at the top, we're only going to look at these columns over here. This is ozone. This is methane. And I show the methane simply because for parcels A, B, C, D, F, G, what we find is that this is Michael's total exposure tracer, if you like. Methane is just going to be oxidized, and the higher up we stay, the more photons we see. So parcel A at the end ends up with least methane. Parcel G that we brought down quickly and then moved along has got most methane, and it's nice and monotonic there. On the other hand, when we look at ozone, the behaviour is rather more complicated. Parcel A has got lowish ozone, but parcel B has actually got the highest ozone, and then there's a bit of a decrease, and there's some variability. So really, the details of the path and the details with which we move along the path are important. I'm just going to show you two final cases, two sort of examples. This is one parcel. This is parcel. Let me show you parcel B first of all. And that's parcel B is the parcel with the highest ozone at the end. So this is ozone versus time. We start off with rather unrealistic conditions. Very quickly, we've established a new steady state, and then ozone follows some kind of seasonal cycle and drops away. Down here is the NO, the NO2, and the NO3. And if we look at parcel C, which is the sort of next parcel down, which has got somewhat lower ozone, so parcel C is the lower one. Well, it's to the beginning it was exactly the same. It was following exactly the same path. And then we see in this region here, this rather short region here, there's a divergence between those two, and this ends up with rather less ozone than that. And the reason it ends up with less ozone than that is a balance between photochemical destruction cycles that are going on and photochemical production. The photochemical production is going to be maximized along our upper path. The upper path has got actually, there's more photochemical destruction as well. NO stays in this parcel longer than the lower path, so we've got less destruction, but we've also got less ozone production. So it's a rather complicated story. The point about the story is it's path dependent, and as I say, what we'd like to do is to look at some real paths to see how well this story stacks up as to how well we might be able to explain some of the changes in mid-latitudes on this, basically going back to this idea of Brewer and Wilson's. Thank you.
This is exactly a problem that I've thought about a long time and never done anything about or even this much. There's a fascinating sort of fundamental point here. What is the total replenishment rate of the ozone layer? Now, in the Brewer-Dobson paper, I guess there was the first estimate of that. Can anyone in this room, you, John, give us an idea what that number ought to be? Because last time I tried to guesstimate it was something like 3 million tonnes per day. Would that be far out?
We have a units problem. We thought of it in terms of molecules per second, I think.
Yeah, I was going to say it's.
What do you reckon it was?
The only person who talks in
I looked it up.
in megatons is Ruben Boschkov, isn't it? But,
politicians and crazy people who say they're going to, artificially replenish the ozone by, some geoengineering process. Yes.
I'm not sure. I don't quite understand the implication of the question, so I'm not sure that I can answer it. Where do you want to? I mean, you're talking about in high latitudes now.
No, I mean the global figure, the total rate at which the ozone replenished. One of the numbers we need to know to have with Lord Kelvin a unique feel for the formula. I never take satisfaction in formulas unless I feel their numerical magnitude. But this is
well, the short answer is I don't know the answer.
okay.
Would it be equivalent to take a model and turn off the production and see how long it took to go away?
But one way was to ask how much is lost to the chromosphere per unit size, yes. In a steady state, they would have